So here we are now on chapter 7. Chapter 7, we're going to be dealing with chemical reactions. By this time, you have already taken test number 2, or you are getting ready to take it. And as you may have seen, you now know how to do chemical names. You know how to do chemical formulas. You are even have been introduced to the mole concept and calculations with the mole. So all that is gonna come into play now with chapter 7 and forward. So everything you learn, like I said on the week opener last week, the foundation is set. Now you're using everything you know. So what objectives are we gonna use on this chapter to keep expanding that knowledge? Well, we're gonna see how we know that a reaction happened, how to see the evidence of a chemical reaction. We learned earlier on the course that matter cannot be created, matter cannot be destroyed, matter can only be transformed. So we call that the law of conservation of matter, which is what balancing a chemical equation means. We don't leave any element behind. Then we're gonna balance those equations. Once we identify if the chemical equation is balanced or not, then we're gonna learn about solubility of compounds so we can start working on a specific type of reactions like precipitation reactions, which is what we're gonna be doing at that point once we know about solubility. And to do that, we're gonna have to be able to write complete ionic equation, basically break the compounds into the ions. So you're gonna be doing backwards what you learned how to do when you were making formulas. And from there, we're gonna be able to get the net ionic equation, which tells us the true story of the reaction, what's really happening. And, and then we can write the complete molecular chemical equation, which describes everything. Then after we're done with precipitations, we're gonna move into neutralization reactions or reaction between acids and bases. And we're gonna see that some of those reactions create gas. So you're gonna have to keep track of which one create gas and which one doesn't. And from there, we're gonna move to another type of reaction, redox or reduction oxidation reactions. And we're gonna see that a combustion reaction or a reaction that happens really fast, creating an immense amount of energy, like fire, are a special type of redox reactions. And with that, we're gonna say that we can classify chemical reactions, most likely precipitations, combustions, redox, and neutralization, acid-base. So we're gonna go deep into different type of reactions on this chapter. So let's begin by knowing that a reaction is happening. How do we know that a reaction is happening? Well, we're gonna see different things. For example, you can mix two chemicals and you're gonna see color changes. You can mix two chemicals or probably apply energy to a chemical and you're gonna see the formation of bubbles. So bubbles are being formed, which means there's a gas is being created. That's what bubbles implies, the creation of a gaseous substance. We're gonna see precipitations or formation of solids, which are gonna be the mixture of two homogeneous solution creating a heterogeneous solution. So all this that you see here, like it's like a powder that will eventually will settle to the bottom like a solid, which is the same thing you're seeing here. This is the different reaction, but the same type of reaction, a precipitation reaction. You're also gonna see that reactions sometimes produce light. That's obvious with a fire or with a chem stick. So you have a chemical stick, you see the formation of light also. And you're also gonna see reactions related to heat or energy. Like a cold pack, when you activate a cold pack by breaking the pouch on the inside. It gets cold because there's a reaction that is absorbing energy. And if you have a heat pad or you're burning something, you see that the heat is being produced. And there's one more that is not here that I wanted to mention. That is when you mix something and you have a new smell. If you have a new smell, it's because something is getting to your sensors or your nose, and that has to be a gas. Piece of advice: if you ever mix something and you see a color gas coming out of it, run like crazy. Most of the color gases are going to be poisonous gases, so keep that in mind. Not all of them, but I wouldn't stick around to check. So those are the signs that a reaction is happening. And that's all we have to know about this concept. So be aware of those signs. So with that in mind, you should be able to answer DailyWare 7.1. And we are done with this first learning objective, which was identify the evidence that a chemical reaction is taking place. Once you know that a chemical reaction is taking place, if you know the chemicals that are involved, then you can write a chemical equation. But, like I said before, matter cannot be created, matter cannot be destroyed, matter can only be transformed. So you can take the elements of a compound, break the compound apart, and reorganize the elements on a different way. So you're transforming, but you cannot lose any of those atoms. Every single atom has to be accounted for. That's what we call a balance equation. For example, let's say that I have a propane, like the one you have on your barbecue grill or a stove or something like that, which is going to be C3H8, and you just trust me on this one. And we know that propane is a gas, so the chemical equation will tell you the state, solid, liquid, gas. And we're combining this with oxygen, which you already know that is a diatomic. So every time oxygen is by itself, it's a diatomic molecule. And it's going to be a gas, and that's basically the oxygen that we have on the air. And when you do that, you're basically burning propane. It's an oxidation reaction, it's a combustion reaction. And when you burn propane, you're going to produce carbon dioxide, which is a gas, and water. But because you have a lot of heat and fire, the water is going to be water vapor, not liquid water. So then we do this. Well, we gotta make sure that we do not violate the law of conservation of matter, right? So I'm gonna have the left side of my reaction, and I also gonna have the right side of my reaction. So this is gonna be the left side, this is gonna be my right side, and I'm gonna keep track so I do not violate the law of conservation of matter. I'm going to keep track of the elements I'm dealing with. So that's another thing. Whatever element you have on the left side of the equation, which we call the reactants, it has to be the same as the element you have on the right side of the arrow or right side of the equation, which we call the products. So these are going to be my products. These are going to be my reactants. So you cannot have carbon, hydrogen, and oxygen on the left side and then suddenly show a nitrogen on the right side. That doesn't happen because you cannot create matter. So it has to be exactly the same elements. So let's do this. On the left side, I'm beginning with 3 atoms or 3 moles of carbon. So if we're talking about only one molecule, then it's 3 atoms. If we're talking about a mole, then it's 3 moles of carbon. And you already know that from chapter 6. And 8 hydrogens and 2 oxygens. On the right side, I have only 1 carbon. So we can see a problem there already. I have only 2 hydrogens and 3 oxygens. So this equation is not balanced because you do not have the same number of elements on the left side, the reactant side, as you have on the product side, or the right side. So we have to force it to be balanced. So that means that we're gonna have to have 3 carbons on the right side, and we're gonna do that by multiplying. The only way we balance equation is by multiplying, which means that on the right side, for the carbon, I just multiply by 3. That doesn't mean this. That doesn't mean I'm gonna multiply by 3. That's not what it means. Wherever the carbon is, I'm multiplying by 3. I just added a coefficient. So we're learning a lot of new vocabulary today. I just added a coefficient to the carbon dioxide formula. So that tells me now that if I have 1 carbon and I multiply it by 3, then I get 3 carbons. So it's balanced now. However, the moment I put that 3 there, that 3, so when I went and did this, that 3 is affecting everything. So I have 3 carbons and 6 oxygens. 3 times 1 is 3. 3 times 2 is 6. So we never balance by changing the subscripts. We balance only by adding a coefficient. So put that on your memory bank. However, the coefficient can affect more than 1 element like we just saw. So the carbon is taken care of. But the oxygen changed, right? So we don't have 3 oxygens. Now we have 3 times 2, which is 6, and 1. So you gotta keep track of all the oxygens on the right side. So now we have 7 oxygens. And the table that we're putting the numbers allow me to keep track of of what I'm doing. So 7 oxygens now on the right side. So let's continue doing this. So we already know which is which. Just clear the screen a little bit. So let's fix the hydrogen. 8, so we need to multiply by 4. On the right side, wherever the hydrogen is, we are going to multiply by 4. So that tells me that I have now 8 hydrogens, but I also have now 4 oxygens, and I already have 6 oxygen. So my hydrogen is okay, but now my oxygen jumped to 10 oxygens. So how can I fix that? Now I'm gonna have to multiply on the left side. So the 2, I'm gonna multiply it by 5. So wherever I have oxygen on the left side, I'm gonna multiply by 5, so which means I'm gonna put a 5 there. And that should be a balanced equation. So let's check it again. Let's clear the screen. Let's clear all my numbers. And we're gonna make sure that it's balanced now with the new coefficients. So on the left side, I still have 3 carbons. I still have 8 hydrogens, but now I have 10 oxygens. On the right side, I have 3 carbons. I have 8 hydrogens, and I have 3 times 2 is 6, 4 times 1 is 4, and I have 10 oxygens. So now, this is a balance equation. So that's how we make sure that we follow the law of conservation of mass. The same amount of atoms that I have on the left side is exactly the same amount of atoms that I have on the right side. Therefore, it's balanced. You didn't create or destroy anything. You now know that for every 1 molecule of propane, you're gonna need 5 molecules of oxygen, which is what you saw on chapter 6. For every 1 mole of propane, you're gonna need, according to this equation, 5 moles of oxygen. So you are creating now conversion factors that you can use in the future to decide or predict how much of a chemical you are gonna need or how much of a chemical you are gonna produce. So balance equations are gonna be another tool that we're gonna use on subsequent chapters. So we continue adding to our mental learning frame. So that's how we're gonna identify that our equation is balanced. That's how we're gonna balance equations, and we're also gonna see how we can write it straight from the formulas. So let's start with this one. List the number of each type of atom on each side of the equation and determine if the equation is balanced or not. That's what we just did earlier. So my advice is, until you feel more confident with it, eventually you should be able to do it in top of your head, always use this table. Left and right, my elements are lead. This is a polyatomic ion like you learned on chapter 6 and 5. If the polyatomic ion is present on both sides, go ahead and write it like it is. If not, break it into the elements. I don't see it on the other side, so let's break it into the elements. Nitrogen, oxygen, sodium, and chloride. That's all I have on my left side. Let's see what I have on my other side. So on my other side, so my left side, I'm gonna have 1 lead, 2 nitrogens, because you have 2 of these, so you got 2 nitrogens, you're gonna have 6 oxygens, you're gonna have 2 sodiums, and you're gonna have 2 chlorides. So we're using the skills you develop on chapter 6. On the right side, we have 1 lead, 2 chlorides, 2 sodiums, 2 oxygens, and 3 hydrogens. There's no hydrogens on my left side. So immediately you can say that equation is a monstrosity. We just created an element. You cannot create elements. So you're not even trying to see if this is balanced or not. You just discover that it makes no sense at all, because you cannot create elements. There's no hydrogens on the left side. How come we have 3 hydrogens on the right side? So you can stop right there. Don't even worry about checking to see if it's balanced or not. It just makes no sense. But you see where we were going with this, right? So the oxygen wasn't balanced, everything else was balanced, but we cannot create a hydrogen just for nothing. At least not with this chemistry. We can do it with nuclear chemistry, but we're not there yet. So that will be your daily work. 2 reactions. Check to see if they're balanced or not. And let me know how many atoms you have of each one of them. So, now that you know about balancing equations, and obviously this requires a lot of practice, let's write equations from a verbal problem. You know how to do formulas now, So let's see the first one. Solid lead Roman numeral 2 sulfide. So I know I'm gonna have lead, which is gonna be 2 plus. How do I know this is 2 plus? Because it's telling me so. The Roman number is telling me so. And I know it's gonna be combined with sulfide. So that would be the first compound. And it's gonna react, so it's gonna add to aqueous hydrochloric acid. And you learn how to name acids on the previous chapter. So hydrochloric acid is gonna be HCl. And it's gonna be aqueous based on what this is telling us. And it's gonna make solid lead 2 chloride. So it's gonna make lead 2 with chloride and dihydrogen, a molecular compound. So dihydrogen sulfide. Okay, so let's put it together. So this is gonna give me, sulfur is 2 minus straight from the periodic table. So this is gonna be PBS. So PBS, which is a solid, so you gotta make sure that it's a solid, reacts with hydrochloric acid, which is aqueous, producing or to form, producing lead chloride. This is -1 straight from the periodic table, crisscross, PbCl2, producing PbCl2, which is a solid according to the problem, plus dihydrogen sulfide, which is a gas according to the problem. So now all we have to do is balance the equation. So first thing, let's make sure it makes sense. Do we have lead on both sides? Do we have sulfur on both sides? Do we have hydrogen on both sides? Yes. So every single element on the left is represented on the right side. So let's do that. Left side versus right side. The elements are going to be lead, sulfur, hydrogen, and chlorine. Let's keep track of all these. So on the left, 1 lead, 1 sulfur, 1 hydrogen, and 1 chloride. On the right, 1 lead, right? 2 chlorides, 2 hydrogens, and 1 sulfide. So the lead is already balanced, the sulfur is already balanced. Let's multiply on the left side for the hydrogen. So wherever the hydrogen is on the left side, I'm gonna multiply by 2 using a coefficient, which is gonna change my chloride also. So this just went to 2, and it's balanced now. So that was easy. Only with one coefficient, we were able to balance the equation. So let's do the next one. So this requires a lot of practice, so we're gonna spend more time on this one than other problems. So this one is done. So on the next one, gaseous carbon monoxide. So carbon monoxide, which is a gas, reacts with hydrogen gas. Hydrogen all by itself is diatomic and is a gas to form gaseous methane and liquid water. Okay, so here we go. Carbon monoxide, which is a gas, reacts with hydrogen, which is also a gas, to form or to produce methane, which is a gas, and liquid water. That's a lowercase l. So let's do our left and right setups. We have carbon oxygen, and hydrogen on the left side, and carbon, oxygen, and hydrogen on the right side. So let's count. On the left side, 1 carbon, 1 oxygen, and 2 hydrogens. On the right side, 1 carbon, 1 oxygen, and 6 hydrogens. That's where the 6 come from. So we have to balance the hydrogen. So we need a total of 6. We only have 2. However, all we have to do is multiply by 3 on the left side where the hydrogen is, and that should give us our balance. So let's double check. 1 carbon, 1 carbon. 1 oxygen, 1 oxygen. 6 hydrogens, 6 hydrogens. So that's how we balance that equation. Let's do number 3. So for number 3, let's see what we're going to do on number 3. Let's go ahead and clear this up a little bit so we can use it for the next one. So for number 3, we're going to have solid iron trioxide. So we're going to have iron 3 plus because the Roman numerals tell us so, combined with oxygen. From the periodic table, oxygen is -2, criss-cross, iron 2, oxygen 3, and it tells us that it's a solid. It's reacting with hydrogen gas. We know hydrogen is diatomic. By the way, anything, I never realized that until I was reviewing the book yesterday, any element that ends on gen or -ine is a diatomic element when it's by itself. So to form or to produce solid iron, so just iron, but solid, plus liquid water. Okay, so let's see if this is balanced or not. We're going to have iron, we're going to have oxygen, and we're going to have hydrogen. On the left side, 2 irons, 3 oxygens, and 2 hydrogens. On the right side, 1 iron, 1 oxygen, and 2 hydrogens. So let's begin with the oxygen. The oxygen, we have 3 on the left side, 1 on the right side. So wherever the oxygen is, we're going to multiply by 3. So we're going to multiply by 3 right there. That's going to affect the water. So the water, therefore, affecting the hydrogen also. So we're going to have 6 hydrogens now. So keep track of everything before you move forward. That means that I'm going to multiply by 3 on the left side where the hydrogen is. And I should multiply by 2 on the right side for the iron. That doesn't affect anything else. And that tells me that this equation is now balanced. So that would be how we balance the third one. So one of the most important things you have to do is to get these compound formulas right. If you start balancing an equation and it doesn't matter what you do, is you cannot balance it, it's most likely because you wrote one of the formulas wrong. If the formula is wrong, like if I put Fe3O2 instead of Fe2O3, the equation will never, ever balance. So if you find yourself struggling with an equation, stop and go check the formulas again. Because once you get the formulas down, it shouldn't be that difficult to balance the equation. It should keep in track of everything. So that would be how we do number 3. So let's do the last one. So for the last one, we're gonna have gaseous ammonia. So NH3 ammonia, which is a gas, reacting with gaseous oxygen, Gen. So it's diatomic, Gen or Ein, and we know it's a gas, to produce or to form gaseous nitrogen, Gen again, so it's diatomic, plus gaseous water. Okay, so we're gonna have nitrogen, hydrogen, and oxygen. On the left side, 1 nitrogen, 3 hydrogens, and 2 oxygens. On the right side, 2 nitrogens, 2 hydrogens, and 1 oxygen. So let's begin with the nitrogen. On the left side, we're gonna multiply by 2. So we're gonna multiply by 2 on there on the where the ammonia is, which is also going to affect the hydrogen. So now I'm gonna have 6 hydrogens. So now let's fix that on the right side. We're gonna multiply by 3 where the hydrogen is, which is also going to affect my water. So this is gonna become at 3. And at this point, it can get complicated. The nitrogen is balanced, the hydrogen is balanced. So how do we balance a 2 and a 3? The easiest way to do this is by using decimals. There are other ways of doing it, but I gotta go straight to the easiest one. We're gonna take 2 and multiply it by 1.5. So whatever the oxygen is, we're gonna put 1.5, which is 3. So it's balanced now. 2 nitrogens, 2 nitrogens, 6 hydrogens, 6 hydrogens, 3 oxygens, 3 oxygens. So this is a balance equation already. However, we cannot balance like that. We have to balance with whole numbers. So 1.5 is our problem. So what number can I multiply 1.5 by that will give me a whole number? And the answer is 2. But I have to multiply the whole reaction by 2. So I'm gonna take the whole reaction, and to get rid of the 1.5, I'm gonna multiply by 2. So when I do that, what do I get? I'm gonna get 4 ammonias, which are gas, reacting with 3 oxygens, 2 times 1.5, which is also a gas, producing 2 nitrogens, which is a gas, and 6 waters. So everything, to get rid of the 1.5, everything was multiplied by 2. So let's see what we have now. 4 nitrogens, 12 hydrogens, 6 oxygens, producing 4 nitrogens, 12 hydrogens, and 6 oxygens. So it's balanced, and there's no decimals on the equation. So that's one of the tricks that you can use to make this easier. Feel free to use decimals, but then multiply the whole equation at the end with whatever number allows you to make the decimal into a whole number. So 1.5 multiplied by 1, that doesn't work. It's still 1.5, right? 1.5 multiplied by 2, 3, stop there. You already got a whole number. So always by the lowest possible number. So with that said, the best thing I can do for you is to allow you to practice. So practice this and then practice some more, and Alex will allow you to practice as much as you need. So that would be the daily work 7.3, which is gonna bring us to a good point to review what we have so far. So we know how to look at an equation now and decide if it's balanced or not. And is it balanced? If it's not balanced, then we know how to balance it now. And given a verbal paragraph with a reaction with the formulas by name, you know how to transform those formulas in those names into formulas. Write an equation with the phases gas, solid, and whatever you need to write, and then make sure that it's balanced. So practice, 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 and that brings us to the first end of our first recording. We are gonna go probably like 3 or 4 more recordings. So more to come. We'll see you soon. Take care.